So next we will discuss about how your embedded system is going to communicate with other devices. So when you are going to have the embedded system, so embedded system will be having the processor inside. So we will discuss about how the processor is going to communicate with the other peripherals. So in embedded systems, it's mainly it is whatever the bus technology here you are going to have. So it is totally different from the bus technology which is designed for 8086 and above. So as we have to, as we know that, so there are different versions of your 8086 processor. So which is 885, 886, 8086, 80286, 80386, 80586. So 80586 start from Pentium processor, as I told already. So next is, apart from the front, it is Pentium 1. It is from 8056, it is Pentium processors. So that start from Pentium 1, P1, P2, P3. So now we are already octa-core. So it is going to use the bus technology which is those designed for x86 precise. So because if you are taking your 886 processors, so 886 processors is going to be used for for real-time systems, so it is going to be used for standalone systems. So the most commonly PC used technology in your normal 886 is PCI. So PCI is stand for peripheral interconnect bus, so which will be seen in the motherboard of the PC. So that is how they have that is how in 886 it will be connected. So if I take the normal PC also, the normal PC will be connected using the PCI bus. So that is peripheral component interconnect bus. Peripheral component interconnect bus. So and it will be the peripheral component interconnect bus will be on the motherboard of the PC. So now if we take the embedded devices will make use of the on-chip bus, because whatever you are going to have the embedded device, that will be into a single chip. So if it is a single chip will be there, inside that particular chip only your system will be designed. So your embedded device will be using the on-chip bus. So that will be internal to the chip. So here the chip refers to the IC. Okay, so IC is nothing but integrated circuit. So in our embedded system we are going to connect by chip. So that is going to perform a dedicated task. That particular that particular chip is going to perform the dedicated task. So this particular embedded devices is going to make use of the on-chip bus. So which will be internal to the chip. Okay, so which is internal to the chip, and this particular on-chip bus allows what it allows. It allows the different peripherals to communicate with each other. So different peripherals is going to communicate with the ARM core. So that means whatever the communication you want to do, you have to communicate. You have to do the communication with respect to the ARM core only. That is with respect to the processor only. So because whatever the operation or execution is going to be done, the execution will be done only in the processor. So that means whatever the communication you have to do with respect to the processor is, so it has to be done with respect to the ARM core only. So that allows different peripheral devices to be interconnected with the ARM core. So now if you take the two buses, so there are two different classes of devices attached to the bus. So if you take if you start discussing about the ARM bus technology, so in the ARM bus technology, there are two different classes of devices attached to the bus. So what are the two different classes of buses which is attached? So first is called as bus master, other is called as bus slaves. So there are two first classes of devices attached to the bus. One is bus master, other is bus slave. So now where the bus master is connected is the first question, and what are the things which are connected to the bus slaves is the second question. So when it comes to the bus master, so now here normally bus master will always be a processor. Okay, so always the ARM processor will be a bus master. That means who has to initiate the initiate a data transfer with the other peripherals. So because if you want to initiate a data transfer, someone has to tell to the peripheral, right? Who has to tell that one? Your processor has to tell. So your processor will be the heart of the embedded system, right? So your processor core is going to be initiating the data transfer. So your busmaster, that normal definition according to textbook, what it is going to give is, so it's a logical device capable of initiating a data transfer with other device across the same bus. But who is going to initiate the data transfer is the next question. So here the ARM processor core is going to initiate the data transfer. So your busmaster will be always a ARM processor core. Okay, so now next is bus slaves. So who are going to be bus slaves? So now bus slaves refers to what? This is also a logical device. So what does those devices capable of? So these devices are capable of what? It is capable of responding to a transfer request from a busmaster device. Okay. So whenever a data transfer is initiated from the core, or whatever the operation it has to perform, the core will be instructing to the peripheral. So now depending upon what type of operation the peripheral has to do, so the peripheral has to respond. Okay. So the peripheral has to respond to the transfer request from the bus master device. So here the bus slaves will be normally peripherals. Okay. So when you talk about the bus or bus technology, it is classified into two. One is bus master, other is bus slave. So normally bus master will be your ARM processor core. Second bus slaves will be your peripherals. Okay. So next, when it comes to bus, a bus will be having two architecture level. So one is the physical level, and the other level is with the protocol. So the first is the physical level, that is going to cover you about the characteristics and the width of the bus which are there. Okay, so when you are going to have the bus technology, so at the physical level, so it will tell you what is the electrical characteristics of that particular bus. So if you start talking about the what are the electrical characteristics of that particular bus, so how much communication can be done at a single instance of time. So maybe normally it may be 16 bits operation it can do done. So that means upon the width of the bus. So if the bus is a 16 bit width, then it is going to do the 16 bit operation. If the bus width is 32 bit, then it is going to perform the 32 bit operation. If the width of the bus is 64 bit, then it is going to do the 62 bit operation. So now the more the number of bits it is going to have. So what will happen? Obviously, this data transfer between the processor and the device will be more, but it has its own limitation. So what is the limitation? Assume that I have my one processor core, for example. So if I have Pentium 1 or ARM 7 core is there, so I will go with a 16-bit bus. Okay. So now if I have the same for the same core, if I'm introducing the 32-bit, what will happen? Obviously, if, the data transfer cannot occur simultaneously in a single clock cycle. Okay, that is your single instruction cannot be executed in a single clock cycle. So obviously, the performance of the processor will go down. So it is simple that. So if you take the normal bus, so normal bus will be having the capacity of 40 people. So for the same bus, if you put 80 people, what will happen? Can the bus go with the same speed? No. So the speed of the bus will be reduced. So I'm not talking about the processor. So I'm just generally talking about your normal bus which you are going to travel in day-to-day life. So if you take the day-to-day life, the bus which you are going to travel, so assume that the bus is having the capacity of 40 people to accommodate and to go smoothly. So if the same bus, if you accommodate 80 people, so obviously whether that particular bus can go smoothly and fast, no, it cannot go fast. The same thing happen here also. So it is nothing but your electric characters depending upon the processor. So that particular bus width will be designed. So the bus width can be either it may be a 16 bit or it may be 32 bit or 64 bit. Okay, so the second architecture level deals with the protocol. So when you are telling of the protocol, that's the rules. Okay, so now what are the rules to be applied? The second level deals with the protocol. So protocol is the liberty which is governing the rules. So now there's some set of rules will be applied there. How the communication has to be established, how much data has to be transferred between the processor and the peripheral at a single instance of time. So this deals with the protocol that is in the second level. So in the second level, that mainly deals with the protocol. So whenever the protocol comes into picture, it is nothing but the rules that is framed. So what it is going to frame, so that is going to tell you that at what fast the communication between the processor and the peripheral has to take place. Okay, so these are the two different architecture level we are going to have. So next, once it comes to bus protocol, so it is going to be divided into some of the bus protocols which you are going to have. So the protocol which you are going to have in your is one is AMBA bus. So AMBA bus stands for Advanced Microcontroller Bus Architecture. Okay, so this is one protocol. So this is going to have some set of features or for example set of rules to be followed in this particular protocol. So this particular protocol is introduced in 1996. So and then it is going to be widely adopted in on-chip bus architecture. So you can see that. So this particular AMBA bus protocol. So it is introduced in 1996 and is widely adopted as the on-chip bus architecture. And it is used for most processor. this particular protocol will be used in most of the ARM processor. So now, whenever the first ARM bus has been introduced, so the first ARM bus introduced were of two. One is the ARM system bus, yeah, which stands for ASB. Other is ARM peripheral bus, which stands for APB. So it's going to have ARM system, and your ARM peripheral bus is going to connect with the different peripherals of the processor. So which is with that particular embedded system is connected with respect to the different peripherals. Okay. So now when it comes to the into the later stages, apart from your ARM system bus and ARM peripheral bus, so your ARM processor manufacturer introduced another type of bus design. So which is that particular bus design, which is called as ARM high performance bus. So apart from your ARM system bus and ARM peripheral bus, the third bus is being introduced. So that particular bus is called as ARM high performance bus. So now, so whenever you are going to make use of this particular bus protocol, that is ARM high performance bus protocol, it is mainly used for the high performance peripherals. Okay, so whenever you are going to have the more performance, the peripheral is having the high performance, then your normal APB or APB will not be able to communicate with that particular peripherals effectively because it will be slow. So if I am accommodating 32-bit and you are sending only 16-bit, then obviously the performance of the system will go low. So now your ASB, which stands for ARM high performance bus, so it's going to be used for high performance peripherals. Okay, so mainly it is used for high performance peripherals. So now if it consider the low performance peripherals which are there, which will the peripherals which are running low at low level. So because when you are talking about your embedded systems, some of the embedded system should interact effectively. Okay, so that means instantaneously they have to give the result. So if they are not giving the instantaneous result, then there will be so much problem will be there. So for example, if you take the C, so some of the systems may be installed at the seashore, like to tell you that when the tsunami is occurred. So at that time, within that fraction of a time, it has to inform to the server. So if that particular if that particular uh, task is not given to the server, then obviously many people cannot be saved, right? So during that those type of operations, you are going to make use of the high performance bus. So there you are going to make use of the high performance peripherals, and you are going to use it. In some of the peripherals where you are connected, so it doesn't require, even there is a slow, even the device is slower, then there is no problem with that one. So if you take your set-top box, for example, so even if the in the set-top box, even if your video is not streamed properly, so then there is no problem. So during that time they are going to make use of the APB at those type of functionalities. They are going to make use of the ARM peripheral bus. Okay, so next, so this is about your ARM bus technology. Okay, so any doubt with respect to the ARM bus technology? So anybody having any doubt? So if we don't have any doubt, we'll just move further. So next, we move the memory. So now, so already you have gone through this particular part in your organization. So just I will brief it out again, how this particular embedded system memory will be designed. So the embedded system will be having even the embedded system will be having the memory. Why it requires memory? The memory is required to store and execute the code. Now, how I have to consider the memory to my embedded system, depending upon what are the factors I have to consider. So I have to compare with respect to the price, and I have to compare with the performance, and I have to compare with the power consumption. So, and depending upon the application of the embedded system, I have to choose my memory. So if my memory has to be fast, what type of memory I have to make use of? So if I want to have the more memory to be installed, so obviously at that time the cost incurred will be more. So at that time, how I have to decide? And also if your secondary memory is used, then it is going to consume more power. Then what type of memory I have to make use of? So now after having that one, so since you are going to make use of the memory to store and execute the code. So next I have to compare with respect to the performance, price and power consumption. So while deciding the specific memory characteristics. So the specific memory characteristics which you are going to have is one is hierarchy and width and type. So if you take the hierarchy of the memory first, so if you take the hierarchy of the memory, which is one of the characteristics, so first it is going to be have the cache. So because the cache memory will be near to the processor. So what the cache includes? Anybody is having the answer? So what the cache includes? Whenever you are going to have the cache, so what the cache includes? So always the cache includes the recently executed instruction. So since it is near to the processor, so the first access from the processor where it is going to see is cache. So if it is having that particular instruction in the cache, it will execute there from the cache itself. Now, so whenever your program is stored and executed, so that means what? So I will switch on the system. I have my program stored in my system, and I have to start working on that one. So where that particular program will be stored? First, the program will be stored in the secondary storage. First, it will be stored in the secondary storage. So whenever you want to start executing that particular code, first the data has to be moved from the secondary storage to the main memory. So now from the main memory, it has to uh, get the data from the main memory to the cache, and from the cache, it will they take the data from the cache, and it will uh, store it in the register, and it will start executing. The processor is going to start executing. So that is what the hierarchy stands for. So hierarchy is what? So first it will be secondary storage. So normally for your syllabus, we are going to have the hierarchy in terms of main memory, main secondary storage, main memory, and cache. But apart from this one, at the top level, you are going to have the registers. But always the registers will be inside the processor only. So even some of the cache, most of the cache will be there reside inside the processor itself. So now, if you take the L1 cache always reside inside the processor itself. Okay. So now, depending upon the memory size. So now, as you can see, if the memory is less, obviously the performance is more. Obviously the performance as well as the cost is also more. Okay, so if you're going with the performance, it will be having the less memory. So now as the memory increases, obviously the performance is also reduced. That means if the main memory will be having more memory compared to your cache memory, so obviously what the distance between the processor and memory will become more. As and when the distance between the main memory and the processor becomes more, obviously the performance will be reduced. Okay, so if it takes a secondary storage, the more the data size, uh, the storage capacity will be more for the secondary storage. So now, if the storage capacity is more, what will happen? So obviously, first the data, if the particular program has to be executed, means what? First the data has to be brought from the secondary storage to the main memory, and from main memory to the cache it has to be brought, and from cache the processor has to take it, it has to start executing. So obviously the performance is going to be reduced. So compared to your cache, your secondary storage will be compared price is less compared to your cache. Since why it is cache? When it comes to the trade-off between the price and the performance. So if you want to have the high performance, the data should be reside inside the cache only. Okay. So if I'm going with the space, then I have to go for secondary storage. So if I'm going with the space, obviously I have to make a trade-off that my performance will get reduced. So that is what the hierarchy in between will be there. So now, if you take say the embedded system, so as I told already, so the faster memory cache is physically located near the ARM processor core. So as I told you all, they should have the memory trade-off between them. So the closer memory is to the processor core. That is more the closer memory to the processor, the more the cost it includes. But it is smaller in its capacity. That is your cache. Okay, best example. So next is the memory is large compared. So it will be around 256 kilobytes to 256 megabytes, depending upon the type of the application which you are going to which you are going to make for that particular embedded system. So normally, main memory is nothing but your RAM. So my RAM, nowadays you are going to get up to 16 GB, right? 16 GB RAM is there. So according to your textbook, so the memory, whatever the value what they were given is up from when the textbook was written. So it was between 256 kilobytes to 256 megabytes. So that depends upon the application which you are going to make use of. So normally it, this particular main memory, so which is nothing but your RAM, which is going to have 256 kilobytes to 256 megabytes. So depending upon the type of the application, so depending upon the type of the application, it is normally generated, normally stored in the different chips. Okay, they are normally stored in the separate chips. So now, how to access the data? So as I told you that in the risk design philosophy, so first the data has to be moved from the memory to the processor, memory to the register, and we have to perform the operation with respect to the instruction. So for that one, what I should have two different types of instruction, which is load and store. So load and store instruction access the main memory. So unless the value is stored in the cache for fast access. So if the my data is not there in the cache, first I need to access the data from the main memory through the instruction load and store. So then I have to execute by taking the data from the cache. Okay. So next is secondary storage after memory. Secondary storage is the last and uh, slowest form of memory. So the example for your secondary storage is your hard disk drive and CD-ROM. So next comes to the width. So if you take the hard disk drive, the secondary storage may vary from 600 MB to 60 GB. So this particular size is when this particular textbook was written. But now we are going to get the size up to terabytes. In terms of terabytes, you are going to get the hard disk. That is nothing but your secondary storage. Okay. So now next comes to the types. So next comes to the width of the memory. So before going for the touch, this way we will discuss about the width. So in the memory width is a number of bits the memory returns on each axis. Okay. So if you take the memory width, so it is going to be number of bits the memory returns on each axis. So now how much data it is going to return? So how much data it is going to return, or how many number of bits it is going to return. So normally when you are accessing the memory, that depends upon the register which you are going to use. So typically, whatever the memory data which you can keep on the memory will be in terms of 8, 16, 32, and 64 bits. So depending upon the type of the processor which you are going to use. So some processor will be having the 8-bit data. Some processor will be keeping the 16-bit data in the memory location. But so normally in each location you are going to have the 8-bit only. Okay. So the memory bit will be having the direct effect on the overall performance and cost ratio. So because if the more the memory bit, obviously the accessing the data will take time. So that means at the time it will reduce the system's performance. Okay. So next is comes the types. So what are the different types of memory which you are going to have? Okay. So there are many different types of memory which you are going to have. So for the form of the memory devices which are going to have is ROM, so which is read-only memory. So it is the least flexible of all memory types. Okay. So it is already, you people have know this already, you have been studied in your AD only. So just I will brief it out once again. So it is least flexible to all memory types. So since it contains the image that is permanently set at production time and cannot be reprogrammed. So that means what I told is this is your RAM BIOS, whatever tell, that is in your motherboard, on your motherboard you are going to have the BIOS system, right? So what it contains, as I told you, that it is contains the basic drivers which your system should have before your operating system is installed. So here also you are going to have the ROM. So that means it is already programmed at the manufacturer time only. So it contains the image that is permanently set or permanently burned onto that particular chip at the time of the production itself. Okay. So and whatever the data you are going to program there inside your ROM, inside your read-only memory, it cannot be reprogrammed once again. That's one limitation. So inside the ROM, what you are going to have, so it cannot be reprogrammed. Okay. So next, whatever the ROM you are going to have, so these are nothing but used in the high volume devices. Okay. So where you are going to use this particular ROM, so this particular ROM will be used in high volume devices. So where these devices will be used, this is going to be used where they doesn't require any updates. You are going to make use of the ROM where you doesn't require any updates or correction. Okay, so it is going to be, this particular ROM is mainly used in your boot code. So as I told in your normal class, normal system will be having the ROM BIOS. Okay, so that means when the system has, whenever the system has to boot, so you should have the boot code in that one. So the boot code will be stored inside your ROM itself. So it's going to be used inside the ROM, that boot code. So just you remember boot code, where the boot code will be residing. Boot code will be always residing inside the ROM. So now another thing which you have to keep in mind is whatever that code you are going to burn inside the ROM, it cannot be reprogrammed once again. Okay, it is permanently set. So, but it can be programmed only one at the production time. So it can be programmed at once only at the production time. So next, when you are going to have, so the next type of ROM memory you are going to have is flash ROM. So flash ROM, so it can be written to as well as read. So it is going to have read write option both. So now what is the limitation here is in your ROM is, so it can be written as well as it's, so what is the limitation is it is slow to write. Your flash ROM is slow to write. So that means since it is slow to write, so it cannot be used for holding the dynamic data. Okay, so it cannot be used for holding the dynamic data. Since in the dynamic means the value of the data will be keep on changing. So now if the data is keep on changing and if your ROM is um, writing the data in slow fashion, then what will happen? Obviously the performance will get dropped. So for that particular reason, so it is going to be, it is not used whenever you are going to have the dynamic data. So whenever you want to make use of the dynamic data, it's not going to be used. So where it is used first is the next question. So if it is not used for holding the dynamic data, the next question arises is where it can be used. Its main use is for holding the device firmware. Okay, so its main use is used when you are going to hold the device firmware. So here the device firmware stands for the OS. So that means basic OS features which are there for any embedded system to start. So that particular firmware will be stored inside your flash ROM. So and it can be mainly used where your long-term data needs to be preserved. Okay, so if your flash ROM where it is going to be used, so your flash ROM can be used whenever your data has to be preserved for longer time. So for longer time, even if the power is goes off. So even when the power is goes off, you have to keep the data to be there. So doing those type of operations when you are performing, so you have to make use of the flash ROM. So if you take the controlling of the flash ROM, the flash ROM reading and writing are nothing but erasing the contents which is there in the flash ROM or writing the data onto the flash ROM. So those two things are completely controlled by the software. Okay, so that you are going to learn when your lab starts. Okay, so whenever you are going to lab starts, we are going to show you how you are going to program it, how we are going to erase it, and how we are going to reprogram it, your flash ROM. So basically, it is going to be long-term data needs to be preserved after even if the power is off. So now here it is the erasing and writing of the flash ROM are completely software controlled. So the erasing and writing of the software is always software controlled, and it doesn't require any additional hardware circuitry. It doesn't require the additional hardware circuitry. So if it doesn't requiring the additional operating circuitry, what it means? So it means that it is reducing the cost. So in turn, it is going to reduce the manufacturing cost. So the next memory which you are going to have is a dynamic random access memory. So this you already have gone through in your basics of your third sem, that is in your computer organization you have gone through. So it is now most commonly used RAM for devices, since it is having the lowest cost per megabyte compared with other types of RAM. Because if you take the other RAM, there is going to have static RAM is there, SRAM is there. Compared to your SRAM, your dynamic RAM cost is less. Okay, so how many for the megabytes which you are going to have, so that when it comes to the other type of RAM, so it is going to be less cost. But what is the limitations it is going to have? So here, whatever the storage cells it is going here it is going to have, it has to be refreshed frequently. That is one limitations which you are going to have in dynamic random access memory. So it needs to have a storage cells which needs to be refreshed frequently. So that is that is limitations which you are going to have. So whatever the electric charge, so that means if it has to refresh means what? So you have to give the electric charge for every few milliseconds. So that we need to have DRAM controller between the controller before using the memory. So next is static RAM. So next is static RAM. So now your static RAM is more faster than the more traditional RAM, but it requires more silicon area. Okay, so compared to the dynamic RAM, your static RAM is faster than the DRAM, but it requires the more silicon area. But what is the limitation is it doesn't require more refreshing. So it doesn't require refreshing. So if it doesn't require means refreshing means what? The access time for SRAM is considerably shorter. So that means the access time will be shorter for this particular duration. So that's for that particular reason it doesn't require refreshing. So whenever the data is accessed faster, obviously the storing the data inside the RAM will not be there, so that the refreshment will also not be there, but it is having its own disadvantage. Why? Because when the power goes off, as soon as the power goes off, the whatever the data is stored in that particular RAM will be vanished. So that is one limitations which you are going to have. But the last thing is the cost of the SRAM will be high compared to your DRAM. So the last RAM which you are going to have is synchronous dynamic random access memory. So it is one of the subcategory of the DRAM. So, but it is going to be running at a much higher clock speed. So, than conventional memories. Your conventional memories are nothing but your ROM, flash ROM, and DRAM and SRAM. So now here, if you take the SDRAM, that is the synchronized dynamic random access memory. So it automatically synchronizes with the processor bus. It automatically synchronizes with the processor bus. Why it is automatically synchronized with the processor bus? Since it is clocked, because it works with respect to the clock cycle. So since depending upon the clocks what you are going to give, so depending upon that one, so your RAM is going to synchronize with the processor itself. So now what will happen at that time? So internally the data is fetched from memory cell first, okay, and it is pipelined here and finally brought out on the bus in a burst. That means in group it is going to be come. Okay, those are different types of peripherals which you are going to have. So next part is peripherals, which are going to have that embedded components which you are going to have. So a peripheral device performs what operation is going to perform. It's going to perform the input and output functions. So before going for peripherals, any doubt with respect to your memory? Anybody having any doubts with respect to the memory? Any doubt with respect to memory? Okay. So now, if you don't have any doubts with respect to memory, let's move on to the peripherals. So with respect to the peripherals here, so a peripheral device, what it performs, so it is going to perform your input and output functions for a chip by connecting to other devices or sensors that are off chip. So that means whatever the peripheral devices is not there on chip and it is connected externally. So for that, if I want to make the communication, that is input and output functionality, if I want to do, so those will be connected to other devices. Okay. So now, what are these peripherals of? And last is your controllers. So each peripheral device, what it currently usually performs a single function. Okay, each peripheral device is going to be perform the single function. So what are the peripherals? So the different peripherals which are going to use this simple serial communication device for more complex wireless devices. So normal say serial communication, what you are going to do, it will be 802.11 standard. So I think you people are studying in that one in your data communication. So that is going to be made use of serial prefers going to be made use of the serial communication device. So that will make use of the standard 802.11 wireless standards. Okay. So now whatever the peripherals you are going to have in your processor, so the all ARM processors are memory mapped. That means it will run only with respect to the address. So memory mapping is what? So each individual peripheral will be having the address. So with respect to the address only, it will communicate. So if it is only if it can communicate with the address only, then it is then your memory should have that particular address to be stored. So our ARM interfaces are memory mapped. So here the programming interface, what it is going to have, it is going to have a set of memory address register. So those address register will take care of the specific address of the peripheral. Okay. So the last linear is controllers here. So what is the controllers are also one of the type of the specialized peripherals. Okay. So whatever the controllers you are going to have, so those controllers are of the specialized peripherals. So in your ARM architecture, what we ARM hardware, we have seen that in the embedded system hardware, we have seen that. So there are two types of controllers which you are going to have. One is your memory controllers, other is your interrupt controller. Okay. So what the memory controller will do, the memory controller is going to memory processor bus. That's what the memory controller is going to do. So the example is cache ROM, RAM, the hardware to access the memory device, your memory devices. Certain memory devices like RAM, it has to power up. ROM has to be powered up. So immediately ROM has to, because the boot code will be stored in the ROM. So for that particular reason, the ROM has to be powered up first. So after that, when other memories will be initialized. Okay. So the next thing which you are going to have is your interrupt controllers. So interrupt controller is when a peripheral or device requires attention. Okay. Whenever a peripheral or device requires an attention, it raises an interrupt to the processor. Okay. So that means I want to work with respect to the I want that some input is coming from that particular peripheral. So for example, the peripherals which you can connect is your keyboard, mouse, printer, display, and motors. Okay. So now whenever you are going to have the keyboard, so you are going to enter. So once you are going to enter some data, so at the time the interrupt controller, what it is going to provide, so it's going to provide the programmable governing policy. Some policies will be made. So by having that policy, what it is going to allow, it is going to allow which peripheral or device can interrupt the processor. So policy will be made, and depending upon the policy, it is going to tell you that which processor or device can interrupt the processor at that particular instance of time. Okay. So depending upon the timing interval, at what operation it is going to perform, what type of interrupt has to be provided to the processor. So it is going to have. So when you are going with that, there are two types of interrupt controllers which are available for the ARM processor. So when you talk about the interrupt controller, so there are two types of interrupt controller which are available for the ARM processor. The first interrupt controller is your standard interrupt controller. Second is vector interrupt controller. So what your standard interrupt controller is going to do? So your standard interrupt controller is going to send an interrupt signal to the processor first. So your standard interrupt controller is going to send an interrupt signal to the processor core when a device requests servicing. That means whenever an external device wants to request the service, so your interrupt controller is going to signal the processor. Now, it can be programmed to ignore or mask an individual device or set of devices. So this controller is going to be uh, is is programmed in such a way that so whenever that particular device is not required, so that not required, so I can ignore the request from that particular device. So that option can be there in your standard controller, but that has to be programmed. So that has to be programmed to ignore that particular request from that particular device. So here the interrupt handle, what it is going to determine, so it is going to determine so which peripheral which device requires servicing. So your interrupt controller is going to tell you that which device requires the service by reading what? By reading the device bitmap register. By reading the device bitmap register of the interrupt controller. So it is going to decide that whether that particular device requires the servicing or not. Okay. So next is the last one is vector interrupt controller. So in the vector interrupt controller is more powerful compared to your standard interrupt controller. Okay. So why it is? It prioritizes the interrupts and simplifies the determination of which device caused the interrupt. Okay, so your entire vector interrupt controller is nothing but the high priority interrupts. Okay, standard interrupt controller. So it prioritizes the interrupt. So that is going to tell that you are going to have the n number of sensors connected to your embedded system. So depending upon the input, what you are going to get. So the action has to be taken by the processor, right? So during that time, which has to be serviced first? From which peripheral is the service has to be served first? That has to be kept in mind. Okay, depending upon the type of the uh, device which you are connected. So the vector interrupt controller, what it is going to call? It is going to call the standard interrupt exceptional handler. So your event, so your every processor will be having the vector table. So in the vector table, what it is going to hold is it is going to hold what are the depending upon the priority, what are the interrupts has to be served. So like that, if you are going to have 0, 1, 2, 3, so which one has to be first vector, which always priority number 0 will be high. Okay, always when you talk about the priority, so the highest priority will be having for the number 0. Okay, so in that particular number 0 vector table, so which is the address it will be storing the address. Okay, so that is what address is it going to store in the vector table. It will hold the address of the peripheral device. So now if the request is coming from that particular device, it will check that which has to be given priority depending upon the address where it is stored. So depending upon that one in the vector table, that particular device will be served first. So that's what the vector interrupt controller is going to all about. So whenever you are going to have the vector interrupt controller, first it is going to refer to the vector table. So after referring to the vector table, so inside the vector table, you are going to have the n number of vector in request priority set will be there for which device I have to give the priority depending listed the priority depending upon the device. So depending upon the request, what it is coming from the device, so that particular interrupt has to be enabled and it has to be served. Okay. So now first, whenever the vector interrupt controller is there, first it will look into the vector table. So what time from which device the interrupt is coming, and we'll check with the address whether when it checks the address in which location it is there, what is the priority level it is there. So it will check that any other process is coming parallelly. Depending upon that one, it will serve that particular interrupt. Okay, so this is how your standard interrupt controller is going to work about. So your standard interrupt controller, it sends an interrupt signal to the processor core. So when an external device requires serving. Okay, so vector interrupt controller is more powerful compared to a standard interrupt controller. So why it is powerful controller? Since it prioritizes the interrupt. Okay, so that completes your um, embedded hardware. So any doubt with respect to the embedded hardware? Anybody having any doubt? So in the embedded hardware, you go through 4 different components. One is your ARM core, controllers, peripherals, and bus. And next, we are going to discuss about the bus. So bus in the bus, we are going to have bus is the limit. It's the technology which is used for communication with respect to the peripheral devices. So your ARM supports several buses. So we are going to have 2 different class of devices. One is your bus master and other is bus slave. Bus master is your processor core. Bus slave is your peripherals. Okay. So next is we're going to have 2 different architecture level. One first is at the physical level. So in the physical level is the but how the electrical characteristics are there. So how much size it can withstand. The second level deals with the protocol. So what are the rules to be followed when you want to transfer the data between the processor and the peripheral. Okay, so next is when you are going with the protocol. So there are different protocol. So there is first is our AMBA protocol, which we have discussed. So the AMBA protocol is ASP, that is ARM system bus and ARM peripheral bus. Apart from that one, you are going to have the ARM high performance bus. Okay. So next is the memory. You are going to have what are the different memory and the hierarchy of memory types of memory and the peripherals we discussed and memory controllers. Okay. So any doubt with respect to your embedded system hardware, you can raise us. So from next class in the next